Welcome. Have you ever wondered how stars, those brilliant beacons of the night sky, produce the light and energy that dazzle us from hundreds of light years away? In this video, we'll journey deep into the heart of stars to uncover the incredible processes that power them and illuminate the cosmos. From the fiery crucibles of nuclear fusion to the mesmerizing dance of photons through stellar interiors. But before we begin, don't forget to subscribe, ring the bell, and give a thumbs up. The story begins in the core of the star, where intense heat and pressure trigger nuclear fusion reactions. Hydrogen atoms collide with each other at incredibly high speeds and fuse together to form helium nuclei. The process starts with the fusion of two protons to form a deuterium nucleus, releasing a positron and a neutrino. Then, the newly formed deuterium nucleus combines with another proton to produce a helium-3 nucleus. Finally, two helium-3 nuclei collide, forming a helium-4 nucleus, the most common isotope of helium, and two protons that can further participate in fusion reactions. These three reactions release tremendous amounts of energy in the form of high-energy gamma rays. As the mass of the products is less than the mass of the reactants, some of the mass is transformed into energy, following Einstein's mass-energy duality. After photons are produced in nuclear fusion reactions, they travel through the dense interior layers of the star toward its surface. Along their journey, these photons interact with charged particles such as electrons and atomic nuclei. In some cases, the photon collides with the particle. During this process, some of its energy is transferred to the particle, and the scattered photon continues its path with reduced energy. However, in other cases, the photon is absorbed by the particle, and its energy is transferred to the particle. Both scenarios lead to an increase in the charged particle's kinetic energy, which contributes to heating the surrounding material. The resulting heat energy propagates gradually to the outer layers of the star and maintains the necessary high temperature for nuclear fusion to continue. The Blackbody is a theoretical object that absorbs and emits radiation at all wavelengths, with its radiation intensity depending solely on its temperature. Stars, like our Sun, are nearly perfect blackbodies. As heat from the star's core moves through its dense interior layers, it eventually reaches the surface, where Blackbody radiation principles apply. According to Planck's law, the radiation's spectral distribution is determined by the star's surface temperature. Wien's displacement law further relates this temperature to the wavelength of maximum emission. Thus, a star's surface temperature influences both the intensity and color of the emitted radiation. Hotter stars emit more energy at shorter wavelengths, such as blue and ultraviolet light, while cooler stars emit more energy at longer wavelengths, such as red and infrared. As we conclude our exploration of how stars emit radiation, we hope you've gained a deeper understanding of the fascinating processes at work within these celestial bodies. From nuclear fusion reactions in the core to the principles of Blackbody radiation governing their emitted light, stars continue to captivate and intrigue astronomers and enthusiasts alike. We encourage you to stay curious and continue exploring the wonders of the cosmos. Don't forget to subscribe to our channel, hit the notification bell, give a thumbs up if you enjoyed the video, and share your thoughts in the comments below. We value your feedback and ideas for future content, so let's keep the conversation going. Thank you for joining us on this cosmic journey, and until next time, keep looking up.